Someone in Palm Beach posted a TikTok today. They captioned it, "You can barely see it, but I felt it." The video shows a houseplant rocking gently back and forth. A person in Hollywood, Florida, shared a video of a water cooler shaking. Someone in Tampa filmed their houseplant moving. And across social media this afternoon, dozens of similar videos appeared. From across the state, items swaying, people looking confused, emergency lines lighting up, all from a single event at 2 p.m. Eastern Time today that most Floridians had no framework whatsoever to understand. Because Florida does not have earthquakes. Except that today it did, and not a minor one. Today, a magnitude 6. One earthquake struck the Gulf of Mexico, what the U.S. government is now officially designating the Gulf of America, at a depth of approximately 26 kilometers beneath the seafloor, with its epicenter roughly 65 miles northwest of the western tip of Cuba. Seismic waves from that event traveled northward through the Gulf Basin, reached the Florida coastline, and continued more than 500 miles inland, shaking people from Sarasota to Tampa to the Florida Panhandle to Tallahassee. The United States Geological Survey has confirmed it. This is the second strongest intraplate earthquake ever recorded in the Gulf of Mexico. The only larger one was a magnitude 4, that struck near Veracruz, Mexico in 1959, 67 years ago. And here's the scientific detail that matters more than either of those numbers, the word intraplate. Because that single word is the reason this event is both rare and deeply informative about a part of the Earth that most people never think about. This is not a story about damage. No significant damage has been reported. It is not a story about casualties. There are none. It is a story about what today's earthquake reveals about the geological history buried beneath the Gulf of Mexico, why the Gulf can produce earthquakes at all when it has no business doing so by conventional understanding, and what that means for the tens of millions of people who live along the Gulf Coast without ever once thinking about seismic risk. Let's go. The first thing you need to understand is what makes today's earthquake unusual and why the word intraplate is doing so much work in the USGS's description. Plate tectonics, the framework that explains why earthquakes happen, divides the Earth's outer layer into a series of large, slowly moving slabs of rock called tectonic plates. The boundaries between these plates are where the action is. Where plates collide, one dives beneath the other in a process called subduction, and you get the world's biggest earthquakes. The magnitude 9 events in Chile, Alaska, and Japan. Where plates slide past each other horizontally, you get strike-slip faults like the San Andreas in California. Where plates pull apart, you get rift zones. The map of global seismicity, the map of where earthquakes happen, is essentially a tracing of where these plate boundaries lie. The Gulf of Mexico is not a plate boundary. It sits in the interior of the North American plate, a vast, thick, ancient slab of continental crust that stretches from the Arctic to the tropics, from the Pacific coast to the mid-Atlantic. Plate interiors are supposed to be stable. The rock is old, cold, and stiff. The stresses that cause earthquakes should be minimal. And in general, that is true. The Gulf is one of the quietest seismic regions in the Western Hemisphere. Only 6 earthquakes of magnitude 5 or greater have been recorded there in the past 76 years. So why did one happen today? The answer requires us to go back in time. A long way back. Not decades, not centuries, hundreds of millions of years. The Gulf of Mexico is a geologically complex body of water with a deep and complicated history. Roughly 200 million years ago, during the Triassic period, the landmass that would become North America was still joined to what would become Africa and South America as part of the supercontinent Pangaea. As Pangaea began to break apart and the Atlantic Ocean started to open, the crust in what is now the Gulf region was pulled apart through a process called rifting. Rifting creates normal faults, faults where one block of rock slides downward relative to an adjacent block as the crust stretches and thins. Then, as geological time progressed and the Caribbean region evolved, a completely different set of forces acted on the same crust. The Caribbean plate, a smaller plate sitting between North America and South America, experienced its own complex tectonic history, including episodes of subduction and collision. Those collision events created compression rather than extension, and the same crust that had once been pulled apart by rifting was now being squeezed together. And here is where something remarkable happens. This geological history was explained with unusual clarity by earthquake geologists Kevin Bradley and Judith Hubbard in their Earthquake Insights publication today. The crust beneath the Gulf of Mexico contains normal faults from the original rifting and thrust faults from the subsequent collision. And because those original normal faults were still present when the collision began, some of them experienced what geologists call tectonic inversion. They slipped in the opposite direction. A fault that was originally a normal fault, where rock slid downward, became a thrust fault, where rock was pushed upward. the same physical crack in the Earth's crust, repurposed by a completely different tectonic regime acting on it hundreds of millions of years later. Today's earthquake occurred on one of those ancient inverted structures. The USGS classified it as reverse faulting within the North American plate, which is the geological fingerprint of thrust faulting, of compression, of rock being pushed upward. This is not new stress accumulating in response to modern plate motion. This is ancient stress, locked into ancient rock, in structures that formed hundreds of millions of years ago, and that retain enough residual stress to occasionally, very rarely, slip. This is why intraplate earthquakes are so difficult to study and so difficult to anticipate. They do not occur on active, mapped, well-understood plate boundary faults. They occur on ancient structures that are often buried deep beneath sediment, that have no surface expression, and that may go centuries or longer between earthquakes. The recurrence interval, the average time between events on the fault that move today, is essentially unknown. We have one data point from the instrumental era, today, and one historical analog, a magnitude 6, zero event near San Cristobal, Cuba, in 1880, 146 years ago, which caused building damage and fatalities on the island. Susan Huff, a seismologist at the USA Geological Survey, was quoted by Scientific American Today on the broader context of this event. She described the Caribbean as having its own smaller ring of earthquake activity, analogous to the Ring of Fire in the Pacific. That Caribbean boundary, the interface between the North American plate and the Caribbean plate, runs south of Cuba and generated events like the catastrophic January 12, 2010 Haiti earthquake. But today's earthquake happened away from that boundary entirely. Howe said this is something that may warrant further investigation from scientists. Earthquake geologist Wendy Bohan, also quoted by Scientific American Today, was direct about what makes this unusual. This quake is in a somewhat unusual spot, and it's pretty large, she said. She noted that no earthquakes beyond magnitude 5, 0, have been recorded within 250 kilometers of today's event. In other words, the 250-kilometer radius around today's epicenter has produced essentially no comparable seismic activity in the modern observational record. The fault that moved today, whatever it is, has not been producing regular, cataloged seismicity that would allow scientists to characterize it. It is, in a meaningful sense, a fault we did not know existed. This is not alarming in the immediate sense. There's no evidence of any increase in the underlying tectonic stress that would suggest more earthquakes are imminent, but it is scientifically important. The discovery of an active fault structure in the interior of the Gulf of Mexico, one capable of producing a magnitude 6, one event, adds detail to a seismotectonic picture that was thought to be relatively well understood. The Jochen Braunmiller, a seismologist at the University of South Florida, noted to the New York Times that even at a distance of roughly 300 to 400 miles from the epicenter, colleagues working in a Tampa building felt the tremor. That extraordinary propagation distance, the ability of seismic waves from a Gulf event to be felt hundreds of miles away in Florida buildings, has a specific explanation that is directly relevant to understanding the regional hazard. The Gulf of Mexico basin is underlain by thick sequences of sedimentary rock, limestone, sandstone, and evaporite deposits that accumulated over the hundreds of millions of years since the Gulf formed. When seismic waves enter these soft, layered sedimentary rocks, something specific happens. The waves are guided, channeled, and in some frequencies amplified. The sedimentary basin acts as a waveguide, directing energy along its axis and delivering it to the surface at distances far beyond what would be expected in harder, crystalline basement rock. This is called basin resonance or basin amplification, and it is the same physical phenomenon that contributed to catastrophic damage in Mexico City during the 1985 Michoacan earthquake, a magnitude 8. 0 event whose epicenter was 350 kilometers away, but whose long-period seismic waves were amplified dramatically by the soft lake sediments beneath Mexico City. For the Gulf, this means that a future, hypothetical larger intraplate event, say a magnitude 6, 5, or 7, 0, within the range that the historical record cannot rule out, would have its seismic energy channeled northward through the basin with significantly greater efficiency than the same event would in a different geological environment. The soft sediments beneath Florida's coastal communities, particularly the Holocene and Pleistocene age limestones, sands, and clays that underlie much of the Florida peninsula, would further amplify and extend the duration of shaking once the waves arrived. I'm not predicting a magnitude 7, 0 in the Gulf. The statistical base rate is low, but the point is that the Gulf's geological architecture means that events larger than today's, events that remain physically possible based on the tectonic structures we now know exist there, would have consequences for the Florida coastline that standard seismic hazard models, calibrated to areas like California with well-mapped active faults, may not adequately capture. Let me talk about what we can say about the history of this fault zone, because the 1880 event is worth examining specifically. The 1880 San Cristobal earthquake, the most recent event in the Gulf region of comparable size to today's before the 1959 Veracruz event, generated shaking that was felt across the Florida Straits in Florida, caused building damage across western Cuba, and resulted in fatalities on the island. In 1880, Cuba's building stock was unreinforced masonry and adobe construction. The fatalities reflect the vulnerability of that construction to seismic shaking, not necessarily the severity of the shaking itself relative to what 21st century engineering standards can withstand. Today's event, occurring at essentially the same location and magnitude as a 1880 reference point, produced no fatalities and no reported structural damage. This is partly because the epicenter is offshore and far from major population centers on the Cuban side, and partly because modern building construction in Florida, which absorbed most of the energy that reached populated areas, is designed to significantly higher standards than 19th century Caribbean construction. But the 1880 comparison also illustrates something important about recurrence. Two comparable events in the same geographic region, 146 years apart. That is one data point on a recurrence interval, and one data point is statistically meaningless for estimating future frequency. The true recurrence interval on whatever fault moved in both 1880 and again today could be 100 years, or 500 years, or 2,000 years. We do not know. And because we do not know, the appropriate response is not to assume the interval is long enough that we need not worry, but to acknowledge the uncertainty and factor it into how we think about Gulf Coast hazard. The USGS initially reported today's magnitude as 4, which would have tied the all-time Gulf record, before revising it downward to 6. 1, as more seismic stations contributed data. That revision illustrates the iterative nature of earthquake magnitude determination and is routine. It does not change the fundamental significance of the event. I want to discuss the Miami response specifically, because it illustrates something important about how dense urban environments respond to distant seismic events. According to reporting from Quartz, Miami's Metrorail service was temporarily halted following the earthquake. The county's emergency department ordered precautionary evacuations of certain buildings. Emergency lines in several Miami neighborhoods received calls from concerned residents. These responses were precautionary. There was no confirmed structural damage to any Miami building or infrastructure, but they reflect the fact that Miami, unlike most Gulf Coast cities, has essentially no experience with earthquake response, and that the protocols for responding to felt earthquakes are less well developed than they are in California or the Pacific Northwest. Miami is a city of glass high-rises built primarily on reclaimed wetlands and limestone fill. The soft, unconsolidated soils beneath significant portions of Miami's urban core would amplify ground motion from a larger Gulf event in exactly the same way that soft soils amplify shaking. In other basin settings, Miami's building codes include very limited seismic provisions because seismic hazard models for the region have historically assigned low probability to significant earthquake shaking. Today's event is a data point that should inform a re-examination of those assumptions. Jochen Braunmiller, the USF seismologist, estimated from his Tampa building, 300 to 400 miles from the epicenter, that the shaking he and his colleagues felt was likely around intensity 3 on the modified Mercalli scale. Noticeable shaking, perhaps some objects moving but not causing fear or damage. In the epicentral region, intensities would have been significantly higher. For a magnitude 6, 1 at 26 kilometers depth offshore, the shaking intensity at the Cuban coastline closest to the epicenter could have reached intensity. Fase to 7th, strong shaking, potentially causing minor damage to vulnerable structures. Cuban state media reported no major destruction, though officials noted data collection from certain areas was still ongoing at the time of their statements, according to ABC News. No tsunami resulted from today's earthquake. The National Tsunami Warning Center confirmed no tsunami danger via their official X account. The explanation for why no tsunami occurred connects directly to the physics of the event. Tsunamis are generated when the seafloor experiences sudden large-scale vertical displacement, when a large segment of the ocean bottom moves upward or downward rapidly, displacing the water column above it. This most commonly occurs in subduction zone earthquakes, where one tectonic plate is being pushed beneath another and the seafloor can shift by meters in a matter of seconds. It can also occur in intraplate settings, but requires larger magnitudes and shallower depths. The WWSB analysis was precise on the threshold. A damaging tsunami generally requires a magnitude above 6, 5 at a depth shallower than approximately 20 kilometers. Today's earthquake was magnitude 6, 1 at 26 kilometers depth, on both counts below the typical threshold for significant tsunami generation. The nearest fault line to the epicenter is located south of Cuba, where the Caribbean and North American plates meet. The fault that generated today's earthquake is an intraplate structure that lacks the geometry necessary to efficiently generate large ocean waves. This does not mean the Gulf is immune to tsunamis. The 2018 Gulf of Alaska magnitude 7. 9 intraplate earthquake generated a small tsunami, demonstrating that intraplate events can produce wave action under the right circumstances. And there are other tsunami mechanisms relevant to the Gulf, including submarine landslides triggered by earthquakes along the Gulf's continental margins, that are independent of the tectonic mechanism of today's event. But for today's earthquake specifically, the combination of magnitude, depth, and fault mechanism put it comfortably below the threshold for tsunami generation. Let me address directly what today's earthquake tells us about future risk in the Gulf region, because this is the question that matters most for people living on the Gulf Coast. The truthful answer has two components that are in some tension with each other. The first component, today's event does not indicate that the Gulf is becoming more seismically active. 1 magnitude 6. One earthquake, occurring on an ancient intraplate structure, does not represent a change in the background seismic regime of the Gulf Basin. The geological forces driving it are the same forces that have been operating for hundreds of millions of years. This is not a warning sign of anything imminent. The second component, today's event demonstrates that the Gulf can produce magnitude 6 class earthquakes, that those earthquakes are felt hundreds of miles away across Florida, that they can disrupt urban transportation systems and prompt building evacuations in major cities, and that the historical record contains comparable events with damaging consequences. The assumption that the Gulf is seismically inert, an assumption baked into most of the Gulf Coast's building codes, infrastructure design standards, and emergency response planning, is not fully supported by the geological evidence. These two components are both true simultaneously. The risk is real, but the probability of a damaging event in any given human lifetime is low. Low probability does not mean no probability. And in a region where tens of millions of people live, where critical infrastructure has been built without seismic provisions, and where earthquake response protocols are essentially non-existent, even a low probability, high consequence event deserves more attention than it currently receives. The Gulf of Mexico is not the Cascadia subduction zone. It is not the San Andreas fault. It is not going to produce a magnitude 9, but today it produced a magnitude 6. Well, one that was felt across an entire state and disrupted a major metropolitan area. In 1880, a comparable event caused building damage and fatalities in Cuba. What those events share, and what the geological record suggests will continue on timescales that human planning horizons should care about, is that the Gulf is not silent. Its ancient faults retain residual stress. And very occasionally, that stress finds release. Today was one of those occasions. The next one is unknown. The preparedness for it is, across most of the Gulf Coast, essentially zero. That is the terrifying part. Here is what the science actually recommends for Gulf Coast residents, based on what we know today. Understand that earthquake preparedness is not only for California and the Pacific Northwest. If you live in Florida, Louisiana, Texas, Alabama, or Mississippi, and you have never thought about earthquake safety, today is a good day to start. Not in a panic, in a practical way. No drop, cover, hold on. The correct response during any earthquake shaking is to drop to the ground, take cover under a sturdy desk or table, or against an interior wall away from windows, and hold on until the shaking stops. This is the response that saves lives regardless of whether you're in California or Florida. It takes 3 seconds to execute and requires no equipment. Have an emergency kit. Not because an earthquake is imminent, it is not, but because any natural disaster can disrupt utilities and services. Water, food, a battery-powered radio, a flashlight, and first aid supplies are appropriate preparations for the Gulf Coast's primary hazards of hurricanes and flooding, and they are equally appropriate for the lower probability hazard that today demonstrated is real. Follow any official guidance after a significant earthquake. If you are in a building and feel strong shaking, evacuate to open ground after the shaking stops, and follow instructions from building management or emergency services before re-entering. Precautionary inspections after felt earthquakes are standard practice, not overreaction. And if you are a structural engineer, city planner, building official, or emergency manager on the Gulf Coast, the data point provided by today's event is worth incorporating into your professional assessment of regional hazard. The Gulf's seismic potential is not zero. Today made that clear. Subscribe and turn on notifications for updates as seismologists complete their analysis of this event. Stay safe. And the next time someone in Florida posts a video of a swaying houseplant captioned, "You can barely see it, but I felt it," you'll know exactly why.